Yeah, it's probably everyone, so it's just past 2 now. So yeah, actually this is our final in-person applied seminar of the year. Next week's seminar is going to be online. So yeah, we'll make the most of it, and as usual, have some sweet treats after in the staff room. So yeah, so we've got the pleasure this week of inviting Ivo Peters to Cardiff from the University of Southampton. So Ivo was originally in Twente in the Netherlands, and then had some time in Chicago before coming to Southampton 7 years ago. Also, yeah. So he's worked also in suspensions and fluid mechanics more generally. He's in the aeronautics and the space department as well of engineering in Southampton now. So yeah, we're excited to hear about some of these bubble collapse experiments and theory Ivo's been working on in Southampton. So over to you.
Thank you very much, Tom, for inviting me. Yeah, so it's my pleasure to be here. I think this is actually my first in-person seminar after the pandemic, so don't expect too much. But yeah, so I'm going to talk about bubble collapses in complex geometries. So the most important thing of this slide is just that people work with me on this. So a lot of what I will show is done by my PhD student Elijah Andrews. Lebu did a short internship with me, who's now at EPFL. Yoshi, he's actually the one who taught me how to do experiments with lasers. So greatly I owe a lot to him. And finally, David Fernandez. He's one who actually knows more about like the engineering sides of bubbles, how you can use them to clean, and helps me to kind of like think about some applications. So what I'll start with is just an introduction of why we would care about bubbles, and what I exactly mean by these bubbles, what they are. After that, I'll go through some tools, how we do experiments, what kind of modeling we try to do. After that, we're going to go into the meat of it, and we're going to look at bubbles in complex geometry, starting with corners and channels. Then look at some other geometries, and finally we're going to end with some porous materials and see how bubbles act when they're nearby those. So as I mentioned, why do we care about bubbles? So cavitation has been for quite a long time seen as a problem because it can cause cavitation erosion. So these bubble collapses, they can be very violent, they can damage surfaces. So this is an example how a actual piston of a hydraulic pump is damaged by cavitation. But we can also use cavitation, so it's used very widely in ultrasonic cleaning. They also can help in enhancing chemical reactions because you basically generate free radicals when you have these violent collapses. You can also use these bubbles to pump in microfluidic devices. So there are many more applications out there. But what I'll talk about is basically just a very simplified model. The idea to basically get some kind of fundamental understanding how individual bubbles behave in complex geometries. That's kind of the idea. Because you can imagine that all these things can happen in various geometries. And what we've been looking at so far is basically quite simple geometries, mainly how bubbles act near flat plates. So we want to kind of move beyond that. So just to tell you what I'm talking about when I mention a bubble. So I've mentioned cavitation. So cavitation is basically the formation of a void. And when I say void, this is when I say this is a bubble. So I will mainly say the word bubble, but you can replace this by a cavity or a void if you want. They're being created by either large fluctuations in pressures. So if you make the pressure small enough or even negative, you can tear apart a liquid. And that's how you create a cavity. The other way to do it is by heating a small amount of water, for example. And that's the method that I will use because it's really reproducible. then the thing that I'm actually interested in, so this is how I create them, but one thing that I want to look at is how these bubbles then collapse after I've made them. And this is typically initiated by simply pressure difference, but very quickly it's mainly the inertia which is governing what's happening in the system. The other thing I should mention, if you have any questions during this talk, feel free to interrupt me, because I'm more than happy to explain things more, rather than let you think about what I'm talking about for a long time and then have questions. So anytime you can interrupt. The tools that we use, so how we do experiments and the basic modeling that we do. So I mentioned we make bubbles by vaporizing a small amount of liquid, and we do that with short laser pulses. So these are PIV lasers, which are quite standard in the labs that I'm around. So they generate, so they basically dump quite an amount of energy, typically 10 to 100 millijoule in a very short period of time, so typically 6 nanoseconds. So what this means is that the power that you're actually producing is very high. So if you do the calculation, you find that that's 3 megawatts of power which is coming out. It's only very short, but it's a lot of power. Then what I do is I focus this spot down to a very small area. So the irradiance is extremely high. It's 10 to the power 18 watts per square meter. Only a small amount of this is actually being absorbed by the liquid, but that's still more than enough to locally just basically turn your liquid into a plasma and then a vapor. So that's more than enough energy to generate a bubble. That's the main story of this. So this is what it looks like in the lab. So the lasers on this side go through a mirror microscope objective and use a bath of liquid to generate a bubble. By now we have a slightly improved method of this. So right now we use a parabolic mirror, and this is mainly because with a parabolic mirror you can get a much higher numerical aperture than with microscope objective, and that basically increases the reproducibility of your experiments. I can say much more about it, but the eventual point of this is that you have this experiment, you shoot your laser, and you can see when the laser is shot, you see suddenly this cloud of bubbles appear. This cloud of bubbles appears because initially we only make one bubble, but then there are shock waves going around and they nucleate all kinds of stuff around there, and this is why you see this bubble cloud here. But if you look at this experiment through the high-speed camera, recording at 100,000 frames per second, then this is what you see. So just very nicely one bubble being created, grows and collapses. And this whole sequence of growth and collapse, this takes 0.22 milliseconds. So while you blink your eye, such an experiment can happen multiple thousands of times. So that's it for standard expansion and collapse. So this is our experiment. Now I want to introduce you quickly the tools that we use. So the main tool is potential flow analysis. So we assume there's no compressibility. There is compressibility, but in the part that we are interested in, there is not. We assume there's no viscosity. We can say that because things are happening in very short time scales. And so what we can do is define a velocity potential and just basically that's related to the velocities in our liquid. And this means that we need to solve the Laplace equation. Actually, I don't even have to do it because I know that this is one solution, and this is basically the only solution that I need in this problem. And so this is the solution for a point charge. So if you look at the fluid dynamics, this means a sink flow or a source or a sink. And the idea is that if you look at the bubble, this is perfectly radially symmetric. So if a bubble grows or collapses, if it collapses, it's just a radial flow inwards. So we say we can replace this by flow of the sink. One nice trick that you can do once you know you come up with sinks is that you can introduce image sinks. So this is the flow field of the sink. What I'll show you now is just the same vectors but just normalized, so it's easier to see in which direction they're going. And if I put now another sink here, and I call this an image sink. It's called an image sink because it basically represents one sink near a wall. Right, and all this wall is doing is just imposing a no penetration boundary condition. We have full slip here because that's because we don't have any viscosity. So if you now look at the actual vectors again, what you can see is this flow around this bubble is not axisymmetric anymore. This would suggest that then the collapse of this bubble would also not be axisymmetric. So what this suggests is if you have a bubble near a wall, the collapse is asymmetric. And that is indeed what you see if you would run the experiment near a wall, which is this dashed line. The bubble then forms a jet towards the wall. One observation that you can make if you look in a bit more detail, so this is near a wall, this is just an infinite bath fluid, is that most of the collapse is actually axisymmetric, or spherically symmetric. So definitely the expansion, you can barely see any difference with the fully symmetric expansion. And if you look at the collapse, the initial collapse is definitely the same. In the end, there's a clear difference. If we zoom in into this bit, you can see that even there, a large part of this collapse is actually fairly symmetric. Only in the last 2 to 4, 0.02 to 0.04 milliseconds, you clearly start to see an asymmetry. And so and the main point of this is that this is really good news for us, because this means that we can maybe model this collapse without taking into account that this bubble is collapsing asymmetrically, or that there's displacement during the collapse. And that would make our analysis much, much easier. So these are the points that I just made. So most of the collapse is spherical. You can model it as a sink. And if you have a wall, then a jet is generated towards it. If you can remember these things, then the rest will be a breeze. So now we're going to look at bubbles in corners and channels. So I've shown you now a bubble in an infinite bath of fluid. I've shown you what happens if you have a bubble near a wall. And we saw that here a nice jet is generated. One thing that connects these two cases still is that they're both axisymmetric. Right? So even when we saw this jet being formed here, it was very asymmetrically collapsed, but it was still axisymmetric. And one thing you can do to make this situation not axisymmetric anymore is to simply introduce another wall. Let's say that we put another wall here so that we basically have a bubble in a 90-degree corner. So if we look at, so this is the movie that I've shown you, right? So we have a spherical collapse. Here we have a non-spherical collapse, but it's still axisymmetric. And the question is, what will happen if we put another wall here? Right? So one of the first questions you might ask is, do we still get a jet like this? Right? Because this jet, the structure is axisymmetric. And there's no specific reason why this would generate a structure which is axisymmetric. It actually does. So a jet is still formed, and it is fairly axisymmetric. Look at the shape of this bubble. So this was already found by Brujan et al. So we don't have to answer that question anymore. So that's solved. So what I'm going to focus on is these two questions. What can we say about the direction of this jet? And if we can do that, can we extend this then to other corner angles if we are able to solve this? So this is how I set up the problem. We say we have a bubble somewhere at some distance r and angle with one of the walls. So that defines the position of our bubble. And then the thing that we're going to want to find out, or what we're going to measure, is simply the angle that the jet makes with respect to the other, this wall. So these are the geometries that we use, basically 2 glass slides that we put in our experiments. And then if you do, these are multiple experiments laid on top of each other, so you get basically this different positions. You can measure the jet angles, and we get quite a well-behaved system. One thing, or 2 things that we can already say is that there appears to be no dependence on how far away from the corner you are. So it's if you are here, it's the same as if you are here, and there's no dependence on the bubble size. So you could also see that these 2 things are kind of not connected. So these experiments, they are done at different positions, different bubble sizes. And the only thing which matters is the angular bubble position, right? So with respect to one of the walls. So we can make some very quick predictions, which is say if we are close to very close to one wall, we expect an angle of 0 degrees, so it's just going straight to this wall. If we move in the center, we expect something which is purely symmetric, so it goes straight down in this case, on an angle of 45 degrees. And if we move very close to the other wall, we expect again to end up having a jet directly towards the wall. But of course, you can already see that it's not a straight line that's connecting these points. So is there something that we can say about where this curve, this line is coming from? So here we move towards the modeling. So we're going to say again, so we have this bubble. We model it as a sink. So this is our 90-degree corner. And so if we have a wall, then we know we have to put simply an image sink to represent this wall. And if we now also want to represent this wall, then we basically put an infinite wall here, and then we get 2 image sinks on the other side. And then we can look at the flow field of this. And then, so this is the bubble that we are interested in. We want to know what is the overall flow field around this bubble doing. So the trick for that is to basically remove this sink, this one, and then just look at the resulting velocity vector there. And the argument is that this velocity vector will basically tell you which direction your jet is going. Right, and once you have this model, then you can just move this sink around, and the image sinks will move around accordingly, and then you will end up with this curve. So again, so this is the position of the bubble, and this is the angle that the jet is making with one of the walls. And this very nicely fits with the experimental data, so that works. Then, of course, you can think about, okay, can we do this for more corner angles? You probably realize that you need to pick your corner in such a way that you can rotate it and that it matches on top of each other, on top of itself again. So we could think about, could we maybe do this with 120-degree corner, 60-degree corner, or other ones? So let's start with this one, 120-degree corner. I'm just going to go through the procedure that we did with the 90-degree corner. So we're going to mirror this wall, so we get an image sink. So we're going to take this wall here, and that will also now we have 2 image sinks, and now we're going to take the third wall, and that will put the remaining image sinks into our solution. However, if you look at this now, this wall here was originally not there, but we had to do that because we can only mirror things along infinite walls. So what this basically means is that this is not the solution that we try to get for our 120-degree corner, but this is effectively the solution for a 60-degree corner. So apparently we cannot do this for 120-degree corner because we will just end up with a solution for a 60-degree corner. And this image more or less shows that if you look at, say, this is our geometry, that you need to have no penetration boundary condition along these line, along this line and along this line. It's not that clear along this line, but you have to believe me that that's the case. But that's also fine. So we can say something about the 60-degree corner. And so once we have this, then we can also do the experiments. And if you do the experiments, we see that also very nicely matches this prediction. So that works pretty well. I was actually surprised how well this worked. And then, of course, you can go crazy once you understand this step. Right? So this is just a wall image sink. This is our 90-degree corners, 4 image sinks. So 60-degree corner, we got total of 6 sinks. And then you can just continue this process and basically make this corner smaller and smaller. Of course, what you realize is that the only corners that you can look at is basically pi over n, or 180 degrees over n, where n is just an integer. So these were the solutions that we actually tested. You can write this in the equation. Not sure why you would want to do that, other than that you have to spend a lot of work writing this down. But one advantage is that you now can very quickly do the calculation, so you don't have to set up the problem with and look at the velocity fields. You just have an equation which directly gives you the velocity vector. So you can very quickly just make as many curves as you want. And then the question I had was, if we now would normalize these curves, would they kind of collapse on top of each other? Because that would be very useful. So if they collapse, then you can try to interpolate between corners for which you did not have a solution. So we do that. So this is just how to normalize it. So why do we just grab all of them and we bring them, the ends together? Unfortunately, they don't collapse. You could still try to interpolate. So if you want it, if you're really desperate for a solution for a corner for which you don't have one, you can kind of make a curve which sits in between. But they don't collapse. These are not all the solutions. These are only the first 100 solutions. You can go further. So these are the solutions up to n equals 10,000. What we do see is that if n becomes really large, this starts to look more and more like just a step function. And once you think about it, this is not such a big surprise. So if n goes to infinity, right, you basically make your angle smaller and smaller until you basically reach parallel walls. And if you look at what you would expect a parallel wall to do, it's basically, as long as you're on this part of the symmetry line, you would always expect a jet downwards, because of symmetry. The ball will only say, oh, this wall is closer, so I'm jetting that way, or the other wall is closer, so I'm jetting the other way. So if you look at jet direction, this is exactly a step function if you move from here to here. So this concludes the part on bubbles and corners. So it's published here if you want to read a bit more about it. So we have these solutions for any angle pi over n. We validated the first couple of cases. And if you go to extreme cases, where n goes to infinity, you basically have a solution for parallel walls. There are a couple of subtleties there. So parallel walls are not that easy. But you can imagine cases where this would work quite well. Then this is the other part where we're basically using image sinks. So I'm not going to go into any detail here other than show you this picture and explain how this is formed. So it's basically the same method. So you have some geometry and you try to place your image sinks in such a way that you solve for the no-slip boundary conditions of the walls. And what is shown here is basically patterns of sinks. And what's the case in all these cases? If you take one of these lines, you can basically mirror the whole distributions of images on the other side. Equally with this line, it's a perfect mirror image of the other side, and this one is a perfect mirror image of the other side. And so Lebu was the one who found these cases where this works, and it's basically the solution for a three-dimensional channel in which you place a bubble. And these are the shapes of channels for which this works. All right, we're doing on time. So 15 minutes left, a bit more. So next we're going to look at arbitrary geometries and anisotropy. So this is what we've done so far. We say we have a bubble and we model our geometry using an image sink. So what my PhD students did was say, I want to do this like more like a numerical method. So we said, well, we can generate more and more image sinks, but instead of saying an image sink has exactly the same strength, all these sinks, they have some specific strength, and we adjust the strength in such a way that we still have this no slip, no penetration boundary condition on our walls. Right, so in this way you can very well approximate the scenario that we had before with just one image sink, only much more complicated. But this has, of course, the advantage that once you do this, you can adjust this for any geometry that you want. And so you develop this, and so this is what it looks like in 3D, because you need to do this three-dimensional. Right, so in all these panels, it's just like a sink distribution where you try to satisfy the no penetration boundary conditions in every center. And so we tested this with a slot geometry, where we find this behavior. Right, so away from the slot, it goes straight down, then it starts to angle away from the slot. This is basically a gap in the plate. Then it starts to angle down again. And this behavior was loads of experiments. And also the numerical solution very nicely reproduces that behavior, which starts to angle away and then back in again. And so this is published here in this JFM. So the reason why I'm showing this, one, because it's very nice work, and also we use now this numerical model a bit further. And before I say what we're going to do with this numerical model, I want to introduce new concept to you. So this is from the group at EPFL. So Butu Supono is the first author, and Mohamed Farhat, BI there. So they introduced the anisotropy parameter, and there's a lot of stuff on this graph, and that's kind of the point. So on this axis is the anisotropy parameter, and the nice thing of this parameter is that if you know the anisotropy parameter, which is basically a non-dimensionalized version of the Kelvin impulse. The Kelvin impulse is kind of like the liquid impulse that's in your system. Once you have calculated this anisotropy parameter, you can say a lot of things about your bubble. So all these different lines, they are like bubble collapse properties, if you will. So one of them could, for example, be the rebound size. Another one is the jet velocity. Another one is the displacement of the bubble between two oscillations. And the idea is once you know the anisotropy parameter, you know all the other properties of this bubble. And so the solutions that you see here, they are for a number of scenarios. For example, a bubble near a wall, or a bubble in a gravitational field, or a bubble near a free surface, but all fairly straightforward systems. So we wanted to know, can we use this anisotropy parameter to say something about bubbles in more complex geometries? So we've looked at a couple of different geometries, like corners, channels, these slot geometries. So can we use this for that as well? That was the idea. One thing that you need to do is you need to have some bit of time information to do this calculation. And what I've shown you so far, right, with these image sinks, these are just instantaneous velocity fields, so they have no time information. So we need to introduce something to get a bit of information about time, so basically how the bubble evolves. And we can do that using the Rayleigh-Placet equation. If you are familiar with oscillating bubbles, you'll immediately recognize this. If you don't, it's just solving the Navier-Stokes equation spherically. And you can include more things like viscosity and surface tension if you want. But here we're just dealing with pressure difference, bit of simplified thermodynamics, and inertia. That's all that's in here right now. And the main thing that we're interested in is that it predicts the initial collapse well, which it does, right? So this blue line is the Rayleigh-Placet solution, and the green line is a number of experiments. And so this gives us our time information during the collapse. And so then we can include that in our boundary element method, so the one that I showed you, which we use for the slot geometries, and we can do this calculation. We can calculate the anisotropy parameter. So then we can go through our database of experiments, and what Elijah did is say, he categorized all the experiments and then did the numerical calculations for all of them to calculate the anisotropy parameter for all of them. And then he picked a bunch of experiments which were sitting at the same value of these anisotropy parameter. So the only thing that all these experiments have in common, they're all in different geometries, but they all operate at the same value of the anisotropy parameter. And what that means is that you then, if you would normalize their size and their timing, they all behave almost identical. So this is just for one value of the anisotropy parameter. If you want to do this for all the values that we have covered, then you get this. So on this axis is the anisotropy parameter. On this axis, we picked one property, which is the displacement between two collapses, or between the initial expansion and the rebound. And we can indeed see that just this anisotropy parameter very nicely predicts the displacement. And it's basically for any of the geometries that we have tested. Which should appear very soon in physical review fluids, and you can find it on archive. Right, so 10 minutes left. I think that should give me just about enough time to go to the last topic, which is porous materials. So here the idea is that we, on one hand, goes back to simpler systems. So we just have a single flat plate. The only difference is now this plate will have holes in it. And then we want to know what happens to the collapse if there are holes in this plate. Initially, I thought this would be straightforward because it's basically sitting in between two systems, right? So if you say there's some porosity, or let's say a void fraction, and the void fraction is infinite, that you just have void, right? Then you would recover exactly this, which is the bubble in an infinite mass fluid. And if your void fraction is 1, so there are no voids in your plate, then you would recover this situation where this is just a solid plate, you just get the jet. And all the other void fractions will just sit somewhere in between, so you just have to interpolate between those two to get the rest of our behavior. So experimentally, this was very difficult. So what I'm going to show you is it's going to be quite brief, but this took an extreme long time to actually gather all this data. But so the questions that we want to ask, first of all, of course, what's the influence of the porosity of the void fraction? Right? We know like the two extreme cases, so what sits in between? But once you do this, you start to wonder, okay, actually I have to think about the size of my holes, because you can generate the same void fraction with lots of small holes or very few big holes. And once you start doing that, you might think, okay, I can put different shapes of holes in my plate. So these are three shapes that we used. We started with just round ones, but then we figured we actually want to try to get to larger void fractions, and with spheres this is not the best way to get high void fractions. And then you also might wonder, it might actually depend on where my bubble sits, right? If my bubble sits like this, above a piece of plate, or if I move my bubble over here, or it sits directly above a hole, this might influence behavior. So these are the plates that we used, just to give you an idea, so like this size, stainless steel, and then you just laser cut a bunch of holes in it. And so the experiments for these two cases are shown here. On this axis, this is the standoff distance. So this is just how far away from the plate you are. And on this axis, this is the displacement. And so what a solid plate does, right? So you generate this jet, but that also displaces your bubble. So what we are measuring just non-dimensionalized displacement. And if you are very close to your plate, which is on this side, you have a large displacement. If you move further away from your plate, displacement decreases. And so far this works. So if you now do this with a porous plate, you get pretty much the same behavior, but just with a bit less displacement, as you would expect, because this shape impedes the flow less than a solid plate, so to say. But then we started looking at the bubble position, and this is why things get a bit more complicated. So these experiments are done at the same void fraction, so the same plate, only with different bubble positions. So here the bubble is positioned in between holes, and on this lower curve, the bubble is positioned right above one of these holes. And we see that indeed there is a very big dependence on this. Of course, as you might expect, if you move far away, so large standoff distances, so you move your bubble far away from the plate, it starts to matter less where you sit, because the bubble kind of sees a larger area of your plate. But this part is, of course, bad news if you want to make some kind of simplified model for this. There's one parameter that I'm showing here, which is W over R naught. It's basically the ratio of the size of the hole over the bubble size. So in this case, the hole is quite a bit bigger than the size of a bubble. So that's, of course, something that matters. But also just to show you the different behavior. So this is right above a hole, and this is right in between holes. And you can see that the behavior is quite different. I also have to say that this is slightly misleading, because here we are so close to the plate where none of this really works anymore. So all the data that we gather is quite a bit further away from the plate. Just to illustrate that what it looks like. Right. So if we actually look at the size of our bubble and the size of our holes, then we can see that if we decrease this number, then this difference becomes smaller. And there's actually another parameter that you also have to take into account, which is basically the area that your bubble takes up compared to a unit cell of your hole pattern. So the way that you can see that, even if your bubble is quite a bit bigger than a hole, if your holes are very far apart, then it would still matter whether you are above a hole or in between holes, because the other holes simply would be too far away to see them. And there's also a bit of dependence on the void fraction in there. So as long as we are a little bit careful, this can work quite well. And to demonstrate even more that it can work quite well, so the plot that I showed you earlier, this is actually combining data above holes and in between holes. And here it's just indistinguishable. So if you're in the right regime, saying that it basically behaves as a solid plate with some adjustment is quite a good approximation. So that's what we then started to do. So we said, okay, we're going to look only at cases where it doesn't matter where our bubble sits with respect to the holes. And we're just going to investigate the influence of the void fraction. So this top line here, this is just a solid plate without holes. And if we move to the bottom, this becomes more and more porous. And so the void fraction is, so just define it, it's the area of a void, so the area of the holes, or the area of the plate. Or you can say it's the area of one hole divided by the area of the unit cell of the pattern. So we can see quite a nice trend. And so maybe there's something that we can do with this. We can make some kind of prediction. And so to do that, we're going to go back to this anisotropy parameter that I introduced. Because we know if we can say something about the anisotropy parameter, we can say something about the bubble behavior during the collapse. So this is the solution for a solid plate. So the anisotropy parameter is 0.195 times gamma to the power 1 minus 2. And so this gamma, this is the standoff distance. So this is the distance normalized by the maximum bubble size. So this is a very nice and simple solution. And so what we're going to say is that for a porous plate, we basically get the same power law behavior, but not this 0.195, but some function of the void fraction. And we already know two extreme cases. So if our void fraction is 0, we just have a solid plate. If our void fraction is 1, it's 0 because so there's 0 anisotropy in our system. And then the only thing that we need to do is basically just find some kind of equation that nicely connects these two extreme points. We do not know how it connects. But this could be one guess of doing this. So this just goes from 1 to 0. And so the bottom line of this that it works quite well. So here's the experimental data is basically doing the experiments, figuring out what the displacement is, and saying if this was a solid plate, what would be the anisotropy parameter? And from that we can then figure out what our G of phi should be. And so this blue line is then basically just saying what is the best fit to this data. And just to emphasize that now we basically have just a very simple equation that gives us the anisotropy parameter for basically any void fraction and any standoff distance. So if you say this is porosity of my plate, this is where my bubble sits, I have to do a few checks. That it doesn't matter where the bubble sits horizontally, but then I can tell you what the anisotropy parameter is. And that will then tell you loads of things like the jet speed, bubble displacement, and all the other things that were in this very complicated plot that I showed you earlier. So it's under review. You can read about this. If you go to this one, this equation will look slightly different, but it's the same line basically. And that's all I wanted to tell you. Relatively on time. So the main takeaway is basically that the sync model works really well in complex geometries. So almost everything that I've shown you is basically using this fact that during a collapse, the bubble remains spherical and remains in the same position quite well for quite a long time. And it's basically setting up this asymmetric flow field, which then is kind of give you a good prediction of what's going to happen during the final bit of the collapse, where all the stuff basically gets amplified. So I've shown you analytic solutions for corners and channels. If we use boundary element method, we can kind of make this generalized anisotropy parameter, which works for, as far as we know, all the geometries that we have tested, basically. And I've ended with the porous surfaces, where we now have single equation that provides an isotropy parameter. And just want to end again with thanking all the people that have contributed to this. And with that, I want to thank you for your attention and ask any questions that you have, answer any questions you have. Thank you.
Yeah, any questions in the room or online?
I think the question is modifications or bubble collapse in with surface cycles. Because obviously bubble collapse happen mostly in either power plants and turbines and such, but like these are like flat roll curves and plane surface.
Yeah.
Not like porous.
Yeah, so the motivation for this was actually to look at the cleaning of filters. But I don't want to say that this is going to solve anything about the cleaning of filters, because if you want to look at filters, there are way more things to make it much more complex. So you have to take into account also flexibility. So people have looked at flexible plates. So you kind of want to combine this with things that are then porous and flexible. And of course, you have to take into account that the filter is not one layer with holes. It's typically multi-layered. It's kind of more like a bulk surface, which has some porosity, perhaps. And we've basically stayed in the regime where things are still easy. So relatively far away from the surface, or it doesn't matter where the bubble is. So if you want to look at the cleaning of filters, you are actually interested in when the bubbles are really close to the surface, like here. But it could say something about, for example, how bubbles far away from the filter migrate towards it. So that would be something that you could start answering with this analysis.
In the case of the collapse in corners, have you looked at investigating the distance you have to go from the corner for the jet to move away from the perpendicular jet of the wall towards the jet that goes in towards the corner as a function of the corner angle?
Let me see what question make a rough guess why it is.
Did show it tonight.
So I mean, so if you are here,
yes,
then it's going to the wall, and how far away you need to be?
So far along the.
Oh, along the wall like this.
Yes. So if you move further away from the corner, that kind of point, presumably, where the jet is perpendicular to the wall.
Yeah, it's this graph.
Is that what you showed?
Yeah.
Yeah. So
Yeah, this angle is this position.
Yeah.
That angle. So,
yeah. So if you are somewhere away, some distance away from one wall,
Yes.
and you would move in this direction.
Yes. So moving away.
Yeah. So that would change your bubble angle position. Right? So the further you move away, the shallower your angle will be. So the further you move in this direction on the graph. That makes sense.
I think the triangles on the graph are like not explicit on the visual.
Yeah, so the only angles that I'm concerned about is like the bubble angle, which is defined as this. Right, so and if you would move parallel with this wall, that would change your bubble angle. Yeah, and then for basically any bubble angle that you can make, there will be a unique jet angle.
Yeah, because on the graph, don't you have a fixed distance? Is that a distance from this origin? Or like these Ds, how do they compare to the R? Is the D the distance from the nearest wall, or is it?
No, so the way that I've done these experiments is basically take position, go horizontally, take another position again, go horizontally, another position, and all
So
of
the
these
D-
with like different bubble sizes.
So the D is like another.
No, so the D, this is the bubble size. So the
Oh.
maximum bubble size. Yeah, sorry. Yeah, so this was just to show that as far as we have freedom in choosing the bubbles that we make, we don't see a dependence. But also if you'd say, look at the non-dimensional distance, so the distance from the corner divided by the bubble size, right? So basically, we just did sweeps like this. So, and now we find as long as they're on the same angle, they will have the same jet angle.
Oh, it's just Yasmin and Katerina said thanks for nice talks. Yeah, I was thinking about angles above 90. You did this thing where you did the fourfold trick, but above 90 that doesn't work, right?
Yeah, because if you make it slightly larger than 90, then it's not going to work because you just continue rotating your shape around until you've filled everything. So and the next one up is basically 120 degrees.
Yeah. And I thought you said that anything above 90 you couldn't do with that image training. Oh, you can.
You cannot.
You cannot. Yeah, exactly.
Yeah, because well, you can do 180 degrees.
Yeah. I wonder if there's some other way of formulating this so you can do these non-integer steps in pi, but also it sounds like you've got kind of singular limits. We saw that one limit leads to a step function. Presumably the other one leads to an inverse step function or something, like as in you choose one wall or another. Both you can imagine parallel plates or fully open plates. It's like you're either close to one wall and then it just does parallel, it just does perpendicular to that.
Yeah.
Or, whichever one you're closest to in your parallel geometry. Anyway, yeah, it's interesting. Sometimes when you got this kind of singular limits, you can move away from having these summation solutions. But it's kind of a variational problem, basically. Yeah. I'm sure there's some mathematicians.
If anyone has any suggestions.
Because it seems like you shouldn't. Obviously, when you draw the diagram, you're limited by this trick. Yeah. But in the mathematics, you probably shouldn't be because, as you saw, it isn't like jumping in odd ways between these different integer angles. Yeah. It should be possible to interpolate in generality.
I had a question about the behaviour methods where you have the slots.
Yeah.
So how do you decide where to truncate your domain? Because you need the property that potential vanishes far away.
Yeah. So just kind of like do brute forces. Make it bigger and bigger, and just make sure that it doesn't depend anymore on the size. Yeah.
What are the boundary conditions at the edge? Is it just free outflow kind of thing?
Yeah. So the idea is that you just make it big enough that it doesn't matter anymore what you do there. So you kind of have to introduce strength of your sinks or of your sink distributions of all these elements. If you go far away enough, then it just becomes very small. So if it's far enough that you can basically start saying and just set them to 0, then you're good. But yeah, the problem of course is if you're far away, you have quite a big surface, and if this big surface is still a very small value. As long as the surface is big enough, it can start an influence. It's not that easy that you say, oh, it's small, so I set it to 0. The only thing that we do is just try it out.
Okay, excellent. Let's thank the speaker again.
Thank you.